In this video, we're going to introduce normalized floating point numbers. These are only part of the floating point number system, but probably the part that you'll encounter most. For our example, we'll use 32-bit floats. But everything we say applies as well to doubles, that is 64-bit floating point numbers, with the exception that more bits are allocated to the various parts of the representation. Floats are designed to store approximations of real numbers. Of course, only a finite set of these can be represented in 32 bits, but it's still a very useful collection of numbers for doing scientific computation. So let's begin. Suppose we have a decimal number, say minus 52.5. We'd like to represent this number as a float. The first step is to turn this decimal number into its binary equivalent. The integer part is easy. Decimal 52 is equal to binary 110100. Now let's look at the part after the decimal point. When we convert a decimal fraction into a binary fraction, we may have a terminating binary expansion or a repeating binary expansion. In this case, decimal 0.5 or 1/2 is equal to binary 0.1. Putting the two parts together, the binary equivalent of minus 52.5 is minus 110100.1. If there had been a repeating binary expansion to the right of the binary point, we just have noted that at this point. We'd need that fact later. This is the binary number we need to represent in floating point format. Floating point is really a version of scientific notation. This is the way that scientists represent very large or very small numbers. You may recall that in scientific notation, we represent our number in a particular form. The sign is either plus or minus. The constant c has one significant digit to the left of the radix point. The base b is 10 for decimal numbers and 2 for binary. The exponent is a positive or negative integer. Let's put our example binary number into this form. Of course, the sign remains unchanged, but we need to adjust our constant so that there's a single 1 to the left of the binary or radix point. That means moving the binary point left by 5 positions. To compensate, we multiply the result by 2 to the 5th. We're now ready to encode this as a floating point number. To do that, we need to encode the sign, the constant, and the exponent. The base 2 is assumed. 32-bit floats have the following form. We allocate 1 bit for the sign, that's 0 for positive and 1 for negative. Since our example number is negative, we'll store a 1 in that position. We allocate 8 bits for the exponent and the remaining 23 bits for the constant. Let's tackle the exponent next. The exponent in this case is 5. We've allocated 8 bits for the exponent field, which allows us 256 different bit patterns. 2 of those are set aside for special use, so we'll actually have 254 different patterns. We'd like to encode both positive and negative exponents. We allow the range of exponents from minus 126 to plus 127 inclusive. Rather than use 2's complement or some other notation, we use what's called a biased representation. That means we add a constant to the exponent we're encoding that's large enough to ensure that the resulting representation is always positive. Another way to think about this is that it shifts the range of exponents to the right so that the set of representations falls entirely within the positive range on the number line. For 32-bit floats, our bias is 127, which has the effect of shifting the range such that the numbers stored are 1 to 254. For normalized numbers, 2 of the possible 8-bit patterns are not used. These are 0 and 255. That is, all zeros or all ones in binary. The effect of this shifting is that we only need to record positive values in the exponent field. To get back to the actual exponent, we simply subtract the bias from the exponent encoding. In the case of our example, we're encoding an exponent of 5. We do that by storing the exponent 5 plus the bias of 127. And this gives us 132, and that's the value we store in the exponent field. The binary encoding for 132 is 1000100. So putting this value into the exponent field, we have the following. The only thing that remains is to fill in the 23 bits of the constant field. In floating point jargon, this field is also called the frac or the mantissa. Recall that the number we're representing is shown here. The constant portion of this number is already in binary form. But notice that the bit to the left of the radix point will always be a 1 for normalized numbers. So there's really no need to waste a bit in the representation by storing it. We just have to remember that it's there implicitly. We only need to store the bits to the right of the binary point. We'll also need to pad to 23-bit positions. Since the number we're storing has a terminating binary expansion with fewer than 23 bits, we pad with 0 in this case. If this had been a repeating binary, or had more than 23 significant bits to the right of the binary point, we'd have rounded the result to fit in 23 positions, using whatever rounding mode was specified. The result in our case is shown here. This is the 32-bit float representation of the decimal number minus 52.5. There's one more thing worth mentioning. 0 is a special case. 0 can't be stored as a normalized number because there's no 1 bit in the representation after which to place the binary point. We stored a 0 with all 0 bits in the exponent and constant fields. The sign can be either plus or minus. The floating point hardware knows that these are equal and treats them appropriately. Thus, the two float representations for 0 are as shown here.